Today we're going to talk a little bit about how we got to where we are, and then we're going to actually start learning how all of this stuff fits together beginning on next Tuesday. Before we do that, you have a free copy of the textbook in PDF form on D2L. You can download it and make notes on it with Acrobat if you care to do that. You can also download the PDF and either use Send to Kindle on Amazon or upload books on Google Play and get it into your phone and make notes there too, as a matter of fact. You can get a print copy if you want one printed on dead trees from Amazon. If you think Amazon is evil, it turns out that Books A Million has it on sale for $21 instead of $25. However, you should expect it will be shipped by book rate and go, from San Francisco the wrong way around the world to get here or something. I should not expect to get it instantly if you buy it that way. So plenty of things you can do. You can buy for $10 a copy on Google Play Books now. You'll be able for $10 to buy a copy on Kindle Monday. But there's no reason why you should do that. You can do almost anything you need to do with the free copy unless you just want a copy printed on dead trees. Okay, so we looked at this slide last time, and we actually kind of stopped with this one. Memory, the place where programs and data live inside a computer, also known as random access memory or RAM, main memory or primary storage. Those words all mean the same thing. Memory holds both instructions and data for the programs that are running. Programs not running, they're not in memory at the time. The smallest unit of storage is 1 bit. It can hold only a 1 or a 0. Claude Shannon, whom you meet, I think, in chapter 2 of the textbook, showed that the smallest unit of information is also 1 bit. The word bit is a contraction for binary digit. So 1 bit, 1 binary digit. In computers, we organize bits into larger units. A byte is 8 bits and is also called an octet. Octet and byte mean the same thing. And then computers get organize those bits into bigger units called words. The word size of a computer depends on the architecture of the computer. Could be 16, 32, or 64 bits. Could be more. And yes, there are some 8-bit computers that work for embedded systems and things like that. Computers usually perform arithmetic 1 word at a time, and the implication of that is that if there are bigger words, you have a faster computer. I can do arithmetic on more bits in 1 CPU cycle. The stored program concept is one of the most important concepts in computing. And the idea is that the same memory can hold both instructions and data. All right, this is one of the ideas that John von Neumann had when he wrote that first draft of a report on the EDVAC back in 1947, was that we can store a program in memory. Before that, computers were reprogrammed by rewiring them. Now there's plug boards to make the rewiring not as painful as it might sound at first, but it was still a big deal to change a program in a computer. By storing the program in memory along with the data, I can change a program as fast as I can load something into memory. So a very, very important concept. Okay, the program counter, and we did this in call and response last time. The program counter holds the address of the next instruction. The slide says keep track of, same idea. All right, I've already said invented by John von Neumann, probably independently invented by a bunch of other people. There is this idea among historians called because it's time. And the historian will say it is time for certain inventions because all of the necessary prerequisites have happened. So you will find simultaneous invention all through history because everything necessary for the invention exists. 3 different people whose names I probably can't remember off the cuff all invented the integrated circuit at about the same time. Kilby, Noyce, and Lehovic all invented the integrated circuit at roughly the same time. Okay, everything we do today with software depends on that stored program concept. We load software into the computer, and the computer does what the software says. So application software is software that fulfills the purpose of the computer. We almost never spend money to buy a computer to run Windows 11. In fact, if I could figure out how not to run Windows 11, I'd be a happy man. We do sometimes spend money to fool around with Linux or something like that, but mostly we buy a computer to do something with it other than run the operating system. So payroll, word processing, solitaire, pictures of cats, whatever. In addition to the application software, all but the very tiniest computers will have an operating system. And it's the job of the operating system to support the applications by providing both an interface to the hardware and an interface to the user. We talked about that concept as a virtual machine last time. And I gave you the example that I could load Linux onto this laptop and have a Linux virtual machine, or load, in this case, Windows 10 and have a Windows 10 virtual machine. The operating system provides that whole long list of things on the slide: the graphical user interface, file management, input and output, memory management, resource scheduling, and we're going to get into resource scheduling when we get to chapter 6 in the book, but that's what lets us run more than one program at the same time, have many different programs open and all doing work. And the operating system might provide at least some security. In addition to the operating system and the application programs, we have communications hardware. Communication channel is a physical connection between computers, but we can also talk about a channel as a logical connection. We use the same word with 2 different meanings. And we'll try to sort that out and disambiguate those 2 meanings when we talk about communications in detail. But wire or cable, fiber optics, phone lines, infrared light, radio waves, all sorts of ways to communicate from one computer to another. There's also interface hardware. The job of the interface hardware is to connect the computer itself to that communication channel, whatever the communication channel is, and we probably call that a network interface controller, or NIC. Communication software has the job of establishing connections from one computer to another, controlling the flow of data, directing data to the proper application. Now think about it for a minute. You're sitting there browsing the web, and in one tab you are looking at this course, and in another tab you are looking at cute pictures of cats. Don't do that. It will harm your grade, okay? But it's the job of the communication software to get the cat pictures in the right tab and the D2L stuff in the other tab. And it does that with a communications concept called a port number. And there's no actual physical port in this case. It's just a number that's part of the packet that gets transmitted to the computer. If you have heard of TCP stack, that's how that all works. And we'll look at both the ISO model stack and the internet model stack when we get to communications in chapter 4. You'd think I would be able to remember that kind of stuff, but it's harder than you might expect. Protocols, another word that you're going to need to be able to use rigorously are the standards that make communications work. So I can come in here and plug my laptop in to the network and to the projector and that kind of stuff, and it all just works, assuming I have the laptop set up right. Even though it's an IBM laptop, it's probably almost certainly not an IBM wireless access point. This is not IBM equipment. It all works together because of the standards called protocols. So how did we get here? 1640s, Blaise Pascal invented a calculating machine, and nobody trusted it. They were sure that it was somehow ripping them off, and people insisted on doing the computations by hand anyway. 1801, a French weaver by the name of Joseph Jacquard, that J is pronounced like a ZH, invented a loom that used punched cards to describe the pattern to be woven. And once you got the punched cards right, you could make that pattern over and over again without even thinking about it. This is a programmable machine. The program is in punch cards, but it's programmable. This is a jacquard tie. The changes of colors are selected by the program that's controlling the weaving loom. Now, in this case, the program was stored in computer memory, not in punch cards, but it's exactly the same idea as a program stored in punch cards. 1854, George Boole, British philosopher and mathematician, invented this thing called Boolean logic. That's the introduction to chapter 2. We talk about that. The algebra of true and false. And because we're talking about true and false, we can map true and false onto 1 and 0 and have the Boolean algebra be an algebra over binary numbers. Now we've got a way to prove things about binary numbers, and that's very important when we get beyond stuff that you could do with a pencil and paper. Charles Babbage, also back in the 1850s, I guess I need to back up and say why. Before radio navigation for ships, there was celestial navigation. That is, you figured out where you were by the position of the sun, moon, stars, and planets. And if you messed up, well, you sort of sailed off into the vast ocean and never came back. So it was pretty important to do that right. There's an instrument called a sextant that would let a mariner measure the angle from horizontal to a particular something like the North Star, and tables in a book called an ephemeris that helps you figure out where you were based on those angles. Well, guess what? The tables in the ephemeris were computed by hand, and anytime you compute something by hand, there's a chance for error. After they were computed, then they were set in type, which made another opportunity for error. So Babbage said, we can do better than that. I will build a machine that does the computations and then produces the type, the set type that we can use to print an ephemeris. And if my machine is programmed right, the ephemeris can be printed free of error. Well, this is an important concept if making a mistake in the ephemeris means you sail off into the sunset and drowned. That was the difference engine, and Babbage never quite got it working. He had a disagreement with the tradesman who was making the gears and wheels about how much this should all cost, and it never got finished. Meanwhile, he got onto what he thought was a bigger and better idea. The difference engine could do one kind of program called the method of differences for figuring out the tables of an ephemeris. The analytical engine, his second idea, was going to be a general purpose computing machine. So the first design of a general purpose computing machine, Charles Babbage, Remember, Pascal's machine was a calculator only. It wasn't programmable at all. Jacquard's loom was programmable, but it only did one thing. It wove cloth. The analytical engine, had it been built, which it was not at the time, was general purpose, programmable. And you know what? A few years ago, some folks got on a tear and built one from Babbage's plans, and it works just like he said it would. The problem was getting it built, which Babbage was never able to do. Augusta Ada King, Countess Lovelace, that's Lord Byron's daughter. You have encountered Lord Byron in English classes, I hope. If you haven't, you probably will. Developed some of the fundamental concepts of programming. So this is all happening in the 1850s, right? Then not much happened between then and the period before and during World War II. Sorry, I appear to be choking to death. By the way, someone is not choking to death if they're making noise, all right? The person who is absolutely silent, that person is in trouble. But as long as there's noise coming out of my mouth, I'm not in that kind of trouble. Yeah, I guess I don't want to get too far afield from what we're supposed to be doing. The Howard Aiken designed this programmable computer out of mechanical parts and relays, took the design to IBM. They built the thing called the Mark I calculator. 1939, a fellow by the name of Atanasoff at Iowa State, I think, and his graduate student Clifford Berry designed this thing called the ABC, the Atanasoff-Berry computer. And it was quite like a modern computer, except for vacuum tubes instead of transistors. The trouble is that the World War interfered. Atanasoff went off to do things about the war effort, and ABC never amounted to very much. 1942 or so, an Army lieutenant by the name of Herman Goldstein, who was previously a mathematics professor or something before being drafted into the Army, said, I have an idea. And the idea that he had was very, very similar to what Babbage had done. Babbage was going to have proposed a machine to compute the tables for an ephemeris for naval navigation. Well, during World War II, we had exactly the same problem, only with artillery. You do not just point a field gun at something and pull the trigger, right? The shell forms a ballistic path, a parabola. And often the target is out of sight and there's a spotter someplace talking to you on a radio. Well, those guns got aimed using printed tables that took into account the type of shell, the type of propellant, and the velocity and direction of the wind, and sometimes even the temperature. All of those tables got computed by hand by a group of mostly women whose job title was computer. And so they were computed by hand, same possibility of introducing error there. And then they were typeset and shipped out with the field guns. Well, guess what? We were producing new kinds of artillery faster than we could produce the firing tables needed to use them. And so we had brand new modern artillery pieces that couldn't be used because the firing tables weren't ready yet. Goldstein says what we need is a mechanical or electronic device to produce those firing tables. And the Army Bureau of Ordnance's munitions, let a contract to the University of Pennsylvania to build this machine called the Electronic Numerical Integrator and Computer, ENIAC. And that was the first general purpose digital computer. Now, Babbage in the 1850s designed a general purpose computer, but it was made out of gears and wheels. This was the first general purpose digital computer. And they did build ENIAC, and it did work, although not before the end of World War II. the first computational problems run on the ENIAC had to do with the hydrodynamic equations of the H-bomb. So for the Lawrence Livermore Laboratory, where they were working on the hydrogen bomb. Alan Turing was a Britisher and really the father of computer science. He was the person who sort of put together the whole idea of computer science. He was doing code breaking for the British military, invented this electronic and programmable computer called Colossus, which probably preceded ENIAC, but we didn't know about it because of the British Official Secrets Act. Nobody knew about Colossus until 1970 or so. 1945 or 46, John von Neumann, and this is a name you do need to know. You are going to need to know von Neumann's name. Proposed an architecture that is still the way computers are designed. That von Neumann architecture is how we design computers today. Von Neumann was responsible for the stored program concept. That is, not only is data stored in the computer's memory, the instructions are also stored in the computer's memory. And, you know, we do that every day, many times, and it just sort of seems like, yeah, duh, that's the way things ought to work. But it was a brand new idea when von Neumann suggested it. Nobody had done anything like that before. The instruction cycle, which we're going to talk about in more detail than you'll ever want to hear probably a little bit later, but essentially John von Neumann said we're going to do things one thing at a time in the computer. Prior to von Neumann, people tried to make computers faster by doing things in parallel, and that turns out to be very difficult. Turns out to be really, really hard. Von Neumann says, put that aside, we'll do things one at a time, one after another, and get rid of a whole raft of problems. And von Neumann also suggested the use of binary numbers, the zeros and ones. ENIAC was a decimal computer. Decimal, base 10 numbers go in, base 10 numbers come out. But, and we'll talk about this one in more detail a little bit later, it turns out that you needed 10 vacuum tubes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, for each one decimal digit. And von Neumann said, you know, if we use those 10 vacuum tubes for binary digits, we can go from 0 to 1023 instead of from 0 to 9. We got much more expressive power out of our digital circuitry that way. Now, von Neumann did not invent binary numbers. It was, what he did was suggest the use of binary numbers in computing. Let's see how I'm doing. I can't tell how I'm doing. Oh well. This is a picture of part of the ENIAC. In the foreground there you can see a soldier standing in front of one of the cabinets. It's taller than the soldier, so 7 or 8 feet tall. And there are a couple of other people there in the background. Will give you an idea of how big that thing was. Filled up a huge room. We've already talked about firing tables. There were about 18,000 vacuum tubes. And a vacuum tube is a picture in the textbook of a vacuum tube. It's something a little fatter than the human thumb, or than my human thumb. It's the only thing that's not fat about me, apparently. A little fatter than the human thumb, and made out of glass with a vacuum inside, so pretty delicate. The other part of the vacuum tube is that it used an electric heater inside that glass envelope to heat the cathode, the negative element of the tube. And like an incandescent light bulb, eventually that heater burned out. It turns out that 18,000 is a magic number because if you have many more than that, tubes burn out faster than you can replace them. Oops. So that was a kind of an upper limit to computation. The post-war era, the transistor was invented at Bell Labs, but independently in a couple of other places, I think. That information is in your book, but not in my head anymore. in 1951, the two electrical engineering professors who built ENIAC under contract to the Army formed their own company, the Eckert-Mauchly Computer Company, which nobody could pronounce, so they renamed it UNIVAC, Universal Automatic Computer. And UNIVAC, the company, and CBS News got together to use the computer to predict the outcome of the 1952 presidential election based on some early returns. Well, the computer was right, but CBS didn't believe them, so the prediction didn't get put on the radio until much later in the evening. CBS could have been the very first ones with the right answer, but they became unsure of themselves. IBM entered the computing business shortly after World War II. They had been making things like time clocks and tabulating machines all along, but started the computer business right after the World War. 1957, I'm a little sprout in elementary school, and Russia launches the first artificial Earth satellite, Sputnik. That scared everybody in the United States witless because Russia was also threatening, this is really the Union of Soviet Socialist Republics at that time, threatening to blow us all up with H-bombs. And so there was a huge push for education in the sciences about that time. 1958, those guys that I named earlier, Jack Kilby, Robert Noyce, and Kurt Lehovic, I did it this time, all independently invented the idea of an integrated circuit. Vannevar Bush, Vannevar Bush is the right way to say that, I have a cheat sheet here. By the way, have you all noticed that there's a little bubble in the upper left corner of the slides on D2L? And if you hover over that little bubble, the little yellow thing, you see the notes that I have on my slides. So none of those notes, my cheat sheets, are secret from you. Okay? However, this one is sufficiently secret that I can't find what I was looking for. About 1945, after the end of the World War, Bush described something that he called a MEMEX, memory extender, and this is something the size of an office desk, and you can see that there are gears and pulleys and wheels and microfilm and all kinds of stuff in there. The idea was to expand the human memory, and it was designed using the technology of 1945. You could have actually built this thing, or at least most of it, about the size of a desk. We finally got that in about 2002 with the Trio handspring, which is the forerunner of the iPhone. Keep all of your stuff right there where you can get at it, and also use it for communicating. So this idea from 1945 took 60 years to turn into something that could actually be used. 1965, Gordon Moore, who at that time worked for Fairchild Semiconductor, wrote a magazine article, and what he said was, I have observed that the density of transistors in integrated circuits doubles about every year to 18 months. And then he stuck his neck out and he says, I expect that to continue for at least 10 more years. So that doubling every 1 or 2 years is the thing that we call Moore's law. It's not like the law of gravity, not a physical law. It's an empirical observation, but it is an extremely important empirical observation. And here's why. The cost of an integrated circuit chip is roughly proportional to the area. Big chip costs more than little chip, right? And that makes perfect sense. If the number of devices per unit area doubles, if the density doubles, either we get twice as much performance for the same cost, or we get equal performance at half the cost. We can either cut our cost in half, holding performance constant, or we can double performance holding cost constant. I'm going to tell you before the end of the class that there is no such thing as a free lunch, but sometimes it looks like we're getting a free lunch because of Moore's law. So he said in 1965 this is likely to hold true for 10 years. Well, guess what? It's 2023 and it's still working that way. And based on what semiconductor engineers know now, Moore's law is likely to survive at least until 2030. So another 7 or so years, still doubling. Things like the FinFET transistor, where there's a three-dimensional transistor with a fin sticking up, it's inventions like that that are extending Moore's law. All right, so what happens in the 1960s and 70s? Digital Equipment Corporation, now defunct, invented the PDP, Programmable Digital Processor #1. That was the first mini computer. Industrial robotics, things that assembled automobiles and did welding. The IBM System 360, and it used to be that every time a company invented a new computer, they put all of their best ideas into it, made it the fastest, biggest, slickest, bestest thing they could, and guess what? That made it incompatible with the previous computer. And that meant that if I buy this biggest, slickest, fastest computer, I have to redo all of my programs. Well, that was actually possible in the period of time. I remember being happy when my salary passed $5,000 a year. And computers had 2 commas in their price at that time. So millions of dollars. And so, yes, you could afford to pay the $5,000 a year programmer to do everything over again. But the cost of the human staff went up as Moore's law forced the cost of the machinery down. And suddenly it was not economical to redo everything again. IBM said, do it one more time. Write programs for the IBM System 360, and you will never have to do it again. We will maintain compatibility as we build new machines. That's a very bold promise. They did it. You can buy an IBM Z-Series mainframe today that will run programs written for the IBM System 360 in the 1960s. And by the way, as soon as IBM did that, everybody else said, duh, what a good idea. And that's why you can run copies of your favorite game programs from 10 or 15 years ago on Windows 10. There are some really old ones you can't run, but the idea of compatibility is quite a big deal. The Defense Advanced Research Projects Agency, which it's a little bit of a schizo agency. Sometimes they have the D for defense in their name and sometimes they take it out, depending on how one feels about the military at any given year. But the Defense Advanced Research Project Agency started internet research in the 60s and 70s. And there were 9 computers on the internet by whatever date's up there, 1970, and almost 200 of them by 1980. We're now talking about billions, right? But by 1980, about 200 of them. The Unix operating system, which is what's behind Linux, really. The Linux story is an interesting one. A professor by the name of Andrew Tannenbaum wrote an operating system he called Minix it was small enough for one student to hold the whole thing in his brain and learn about it. Linus Torvalds decided that he could take Minix and turn it into an operating system that could actually be used for stuff. and that is where Linux came from. Unix itself, the name is a pun. It was developed by the people who were working on the Multics operating system for Honeywell, General Electric, and some other folks, and they decided that Unix was one of whatever Multics was a bunch of. Pocket calculators, the first integrated circuit chip with a complete CPU on it, was invented for a pocket calculator, a 4-bit chip. The Mythical Man Month by Fred Brooks. Fred Brooks was the head honcho in charge of IBM System 360 project, and he wrote this book, The Mythical Man Month, and then 25 years later put out a revised edition. If you are serious about computing, you should check The Mythical Man Month out of the library and read it, cover to cover. And that is much less trouble than it might sound like, because it's a collection of essays. You can read one complete essay in an hour or so, and then put the book away and read the next complete essay the next time you pick the book up. If the library does not have a copy of it, somebody complain to me and I'll buy them one, because they need one. Personal computers, the Data Point 2200, 1971, cost almost $8,000. $8,000 was real money in 1971. And you can't tell from that picture, but it has the same footprint as an IBM Selectric typewriter. And the idea was not to scare secretaries by putting something that was a computer. You give them something that looks like a typewriter with a screen on it. And that worked. 1976, I guess this is not on the slide, the MITS Altair computer was the first personal computer that an individual could reasonably afford. You could buy it as a kit for $200 if you had $200, which I didn't in 1976. Microsoft and Apple got founded in the decade of the 70s. Then, 80s and 90s, Doug Engelbart at the Xerox Palo Alto Research Center invented the mouse, and there is Engelbart's prototype, the first computer mouse. IBM presented their personal computer in 1981. We started getting graphical user interfaces. Commercial email service. There was no email other than if you happened to be at a university before 1980s. Software engineering. Oh man, we'll talk about that a little bit later in the semester, but it turns out that software is hard. Everybody had to have a programming class before you could get in here, so you found out that software was hard, right? If you did any non-trivial programming. The first programming was done to automate existing mathematical formulas. So think about those firing tables in ENIAC. Everything we needed to know about how to do that computation was already known, because there were rooms full of women doing the computations, right? And so it was a matter of taking that information and translating it into computer instructions. That's easy to do. What turns out to be hard is automating something that's never been done before. That turns out to be hard. And the concept of software engineering was we're going to apply the methods of engineering to the development of large software projects. That hasn't worked yet. There are still phenomenal software failures. Malicious software began circulating around in the 80s. Commercial internet service by 1990 or so. By 1999, there were 56 million computers on the internet. The National Center for Supercomputing Applications at the University of Illinois invented this thing called Mosaic. Tim Berners-Lee invented the World Wide Web in 1989. Mosaic was the first web browser that could display pictures. And all of a sudden, you could put your pictures of cats on the World Wide Web, which was not possible before then. The Java language, which sort of went up and is now fading back down, and I think you all probably had to take a Python course, I guess. Does everybody know that Python is named after the Monty Python comedy group and has nothing to do with snakes? Good. Good. Internet use widespread by the 1990s, still not universal, but most everybody. And the movie Toy Story. Why is Toy Story on my list here? Yes?
Was that one of the first computer animated movies? Like full feature-length computer animated movies?
It wasn't really computer animated. They did motion capture. So there were real actors. And by the way, the motion capture was invented by two guys who studied computer science on this campus. This place was called Southern College of Technology in those days, but the motion capture for Toy Story was invented by two guys who worked on it here. And who has seen Toy Story? It's faintly creepy, isn't it? We haven't, at that time, hadn't quite captured what it meant for computers to be lifelike. But they were obviously not cartoons, right? So they're somewhere between cartoon and lifelike, and that was creepy. We've gotten beyond that. 2000s, U.S. Naval Observatory, which is the arbiter of what time it is, right? Very briefly reported the year as 19100 instead of 2000. Before, well, for years and years, programmers used 2 digits to represent the year. And all of a sudden, 2 digits was not going to be enough. And people spent about $1 zillion. The worst thing that happened to me was we had a baby who was 100 years old, according to the electronic medical record. But of course, we were all sitting there watching. What's going to break? That broke, we fixed it, everybody went home. Ho-hum. There was a lot of ho-hum that night. But man, I'm glad I wasn't in charge of the Naval Observatory. Broadband connections, all of a sudden lots of people can get broadband. Wireless standards. You could have wireless stuff before the 2000s. Symbol Technology had their own proprietary wireless system, but if you wanted to use Symbol Wireless, you could use only Symbol Wireless, and by the way, your IBM ThinkPad won't work with it. Now we have standards, and that's why this ThinkPad can talk to that wireless network. Processors that ran at more than 1 gigahertz. We'll talk about hertz and gigahertz as we go along. 285 million internet-connected hosts in the middle of 2000s. By 2005, 100 million websites. Nobody can visit them all. Even Google doesn't try to index them all anymore. They did try, but they've given up. YouTube is launched. I'm now told that YouTube receives several hours of video every second. They got 39 hours a second? Is it? Okay, I believe that. That number just keeps going up too. I mentioned this on Tuesday. There's a Google data center out past Lithia Springs, and you should, they won't let you in, but you should find some pictures and look at them. It'll amaze you. By 2007, there were 1 billion songs downloaded from iTunes, 1 billion copies, right? And the BlackBerry, that's one of the things that was up and back down, but it was essentially a pocket email device. Apple's OS X Windows XP, which was the first kind of real operating system for most people from Microsoft. It was based on the Windows NT technology, not on MS-DOS. Then, 10 years ago, iPad and iPhone. FinFET transistors, that's the thing that I mentioned a few minutes ago as extending Moore's Law on beyond now and maybe to the end of this decade. And you can see a picture of the FinFET on Wikipedia if you care. Not now. Now you're supposed to be listening to me. Okay? Over 1 billion internet hosts, Windows 10, and OS as a service. Now, so far, I don't really know because KSU pays for my Windows 11. Are individuals paying for subscriptions now? Not yet. Okay, that's coming. Mr. Dove was telling me that he has an Adobe subscription. I'm not going to embarrass you by asking how much it costs, but more than I want to pay.
I get it with students, so it's like $20.
Okay, you get it as a student. But if you don't pay, your software quits working. Yow. PlayStation and Xbox, multi-terabyte hard drives. Man, the first disk drive I ever bought was about the size and shape of a washing machine, held 25 megabytes, not gigabytes, megabytes, and cost $25,000, $1,000 a megabyte. And we thought that was great. Enough disk space to swim in. And to put that $25,000 in perspective, yes.
What were you doing in tech around this time, Ron?
I'm sorry, I'm a little deaf.
What were you doing in tech around this time?
I was running the Information Systems Department for the Medical Association of Georgia, which, among other things, was the contractor for the Experimental Medical Care Review Organization, which did medical care review all over the state of Georgia. But to put that $25,000 in perspective, I bought a house at about the same time. It cost $26,000. 25 grand was a lot of money. All right, so where are we? Beginning development of self-driving cars. The Brown self-driving car test is it can go through the drive-through at McDonald's. You think about it, that's a hard problem. You have to stop at the ordering thingy. Then you have to go up to the pay thingy, stop long enough to pay, and then go up to the next window and stop long enough to get your stuff and then drive down the road. That's a hard problem. People do it without even thinking about it. But if you thought about programming that, it'll make your hair hurt. Okay, 2020 is where we are now, Windows 11. Experimental autonomous cars, although not in California anymore. Several of them got their testing licenses revoked after they ran into things. Almost everybody has high-speed internet connectivity. Ubiquitous is one of those 25-cent words. Big data, you can get a bachelor's degree in analytics here at KSU now, which was a few years ago nobody had ever thought of. New applications of machine learning, including things like maybe learning how to do autonomous automobiles, large language models, and generative artificial intelligence. This is ChatGPT and the follow-ons. Adobe has an online AI program that will remove the background from photographs. It'll isolate a person and get rid of the background. It's free. You can find it and test it out yourselves. And let me tell you, as someone who has tried to do it, removing the background from a photograph is hard to do by hand. Okay, I didn't mention the internet earlier. I didn't mention the World Wide Web earlier. I did mention ARPA and the internet. The internet got transferred from the from the military to the National Science Foundation. So NSFNet beginning in 1986. 1989, Sir Tim Berners-Lee at the European Center for Nuclear Research invents the World Wide Web. And what Berners-Lee was trying to do, there were at that time significant and rapid advances in high energy physics. And Berners-Lee was trying to find a better way than traditional scientific publishing to get that information out and about. Well, he changed the whole world. Commercial internet operation beginning in 1995, and things changed just fundamentally. How? Well, there's Metcalfe's law. Dr. Metcalfe received the Turing Award last year from the Association for Computing Machinery for his invention of Ethernet. But Metcalfe said the value of a network is proportional to the number of people you can connect to. And you think about that for just a minute, and you say, duh, sure. I am old enough to remember competing telephone companies. And so the town doctor had two phones, one from Bell Telephone and one from Home Telephone. So you could call the doctor no matter which phone you happened to have. And of course, that diminished the value of each of the two telephone companies and was unsustainable. Now you can reach nearly anybody you might know, and you can do it in seconds. So here's the effect on commerce. In 1985, there were over 20 Delta Airlines ticket offices spread around Atlanta. You know how many there are now? None. You know how many ticket offices Delta has outside of airports in the whole entire U.S.? One. There's one in Manhattan where you can buy an airplane ticket without going to an airport. Amazon, man, they started out with books, expanded to CDs, expanded again to if it'll fit in a box that UPS will take, and expanded again to whatever it is that you want to buy. Standards are those things that assure stuff works together. I mentioned that earlier today and said standards are why this laptop works with all the stuff that is around here. Sometimes they're created by committees. Sometimes a company will create its own standard and it'll get adopted by popular use. Standards are what make computer systems interoperate. We have standards for languages, displays, number formats, communication protocols, and even the shape of that Ethernet plug is standardized, which is why your Ethernet cable will plug into the Ethernet jack of a machine not made by the people who made the cable. Thousands of standards for the internet, upon which we depend for interoperability. We want things to just work when we connect them, and standards are what allow that. This is relatively new. It used to be, if you were a banker, you bought a Burroughs computer, and then you bought everything that you were going to connect to. It also had to come from Burroughs, because nothing else worked. If you bought an IBM computer, everything you were going to connect to, it had to come from IBM, because nothing else worked. Things just work these days because of standards. Everything from screw threads to communication protocols. All right, we're gonna have to move a little bit. I've been flapping my jaw here. Standards come from either official groups or industry groups. Official groups include the American National Standards Institute, which is not a government group, but it is government chartered, and the International Standards Organization. Interest groups include things like the Wi-Fi Alliance and the World Wide Web Consortium. There are a bunch of them. Okay, by 1990, almost all phone switching was digital, and all of the traffic on the phone system, we're now talking about the hardwired phones, right, which almost don't exist anymore. All the traffic was digital except for that first mile between the subscriber's home or office and the telephone office. Computers and phones were separate. It was that handspring trio that was the first thing that was both computer and phone. Now, almost everything, including phone conversations, is transmitted using the Internet protocol. This business of combining voice and other information is called convergence. So, separate technologies converging into one stream. Okay. Robert Heinlein wrote, I think in 1966, the book The Moon is a Harsh Mistress, and the premise is that the telephone switching computer in the colony on the moon suddenly has sufficient connections that it becomes self-aware. But there is a theme in there. There ain't no such thing as a free lunch, 10 staffel. And you're going to find that computing works that way every place there's a place. Everything we do is a study in trade-offs. Standards are important, but they cost money. Somebody has to pay people to develop the standards. I can make a hardwired control unit faster than a software control unit, but it's going to be more expensive. I can have either a fast algorithm that needs little memory, a slow algorithm that needs little memory, or a faster one that needs more memory. And I got 9 minutes. I can do this in 9 minutes. Talk a minute or two about systems and architecture. We talk about systems all the time: computing system, operating system, security system, sound system. We need to define system, of course. And a system is a collection of components linked together to perform a specific function, and ZAP, recognizable from the outside as a unit. Okay? So, linked together, specific function, recognizable from the outside. Everything outside the system is its environment, and systems communicate with the outside through interfaces. So one of you was asking about abstraction on Tuesday. Here is an abstract diagram of a system. The system is within the boundary of that cloud. The environment is everything outside. I have linked together components, and I have a couple of interfaces. So that is the abstract idea of a system. An information technology system might have hardware, at least 2 layers of software, and some interfaces, things like keyboard and screen, printer, network, and so on. We have a couple of different ways of doing architecture of IT systems. Monolithic architecture, that's the mainframe computer. Distributed processing systems, and there are several flavors of those. Client server, 2-tier, 3-tier, a bunch of tiers, or web-based. And peer-to-peer computing, where there is not a central control. Well, here's a more concrete example of a system. I have a CD player, that's an interface for input, the amplifier and the rest of that stuff in the middle, and then a speaker that is the interface for the output. Here are 2 examples of monolithic systems. The mainframe computer, but also the laptop if it's not networked. Everything that happens on the laptop happens on the laptop. Client server, web server, and client, Google. That data center out in Lithia Springs has thousands of rack-mounted CPUs like that. Web-based computing is kind of a misnomer because the web is the interface, not necessarily the computing. So the Banner system that we use for registration is hideously complex database-driven system with a relatively simple web interface. Things like home routers and other appliances have a web interface. And that's what keeps you from having to deal with these things with a command line. Intranets, web services accessible only to a class of people like employees of a company. Often it's a web server that's on the inside of the corporate network and not accessible from outside. We could provide outside access through this thing called a virtual private network, which we see in Chapter 4. Pay sites are not intranets. This slide is out of place, but it's an example of a multi-tier architecture. Then there's cloud computing, and this was formerly called grid computing, and the idea was that computing power would be as accessible as the electric grid made electric power available. Well, grid computing wasn't a real deal back when it was named, and by the time it became a real deal, the name had morphed into cloud computing. The cloud is an abstraction. If you use Amazon Web Services computing, AWS, once again, thousands of pizza box size computers in a data center somewhere. And we can do software or platforms or infrastructure as a service. Okay, there is no cloud. There's only a bunch of computers you don't own, run by a bunch of people you don't know. And it's very important to remember that. About once a month, you will read a story about some company that put all of their stuff in the cloud, and oops, it's accessible on the internet to everybody in the whole world. The state of Georgia did that a few years ago with nurses' licenses. Oops. Okay, how are we doing? The term information technology was used for the first time in the Harvard Business Review article in 1958. The practice, and this is Brown's definition. If it came out of a book, it came out of the book that I read. That I wrote, okay? Integration, operation, and maintenance of hardware, software, communications, services, and infrastructure to receive, transform, store, and retrieve information of all types, and don't write this down, information of all types in an efficient, effective, and secure manner. But we covered a huge amount of ground there. Okay, the systems architect assesses needs, describes functionality, selects systems, and makes everything work. That's sometimes called system integration, and it is a lot of fun. The profession for which you have set yourselves up is going to be a lot of fun. It's also a lot of work. The academic discipline, so says the Association for Computing Machinery, is the study of systemic approaches, they really meant systematic, to select, develop, apply, integrate, and administer secure computing technologies to enable people to do whatever it is they were trying to do. That's not exactly what the slide says, but you get the idea. Once again, information technology, of all of the disciplines, information technology is the one that requires the most breadth of knowledge. You don't necessarily need depth. I told one of you we're not going to design electronic circuit chips, but you need that breadth, and that makes it a lot of fun. Okay, in the last couple of minutes, professionalism. Information technology is both strategic and customer facing. It used to be a back office function, and if you did something wrong, you could just do it over again and nobody would notice. Now we have to have excellent communication skills, so do that writing that's in the homework. Excellent teamwork skills, that's not two guys in a garage anymore. And knowledge of the organization's business. Not only do you have to know about information technology, you have to know about the business in which you are working. I think we have 90 seconds left. Does anybody have any questions? Yes. Deaf, old and deaf. Anybody who wants to learn the Heimlich maneuver, hang in. Anybody who doesn't, we're done. I'll see you Tuesday. Thank you very much.